The James Webb Space Telescope, or JWST, is opening up new frontiers in astronomy, from protoplanetary disks all the way up to the most distant galaxies. JWST operates in the near and mid-infrared, from wavelengths of around 1 to 30 microns, but with a resolution and sensitivity that is more than an order of magnitude better than previous space observatories at this wavelength, such as Spitzer. These wavelengths show us the emission from hot dust and the youngest stars, and in nearby galaxies we can identify stellar clusters and localize the dust emission within molecular clouds, the intensely dusty regions where stars are born. As part of its first year of operations, the JWST has been observing 19 galaxies as part of the PHANGS project. These have been observed in 8 filters, 4 with the near-infrared instrument NIRCam and 4 with the mid-infrared instrument MIRI. As of just a couple of weeks ago, the data have now been completed and we have released these to the community, alongside our data processing pipeline, which is written in Python and is accessible to anyone to use for their own observations or to process data that's already in the archive. Our Cycle 1 treasury, which means that the data are public immediately, observed the 19 galaxies that have the most ancillary data coverage across PHANGS. So this is things like the Hubble Space Telescope optical imaging, MUSE optical integral field spectroscopy, ALMA molecular gas observations, AstroSat ultraviolet, alongside many others. And this Cycle 1 treasury has been led by Janice Lee, Karen Sandstrom, Adam Leroy, Ava Schinnerer, Dave Thilker, and Kirsten Larson. So, as an overview of the data that we are getting and releasing with JWST, here is an example of the observations for one of our galaxies, NGC 628. So the top row shows the NIRCam observations, the bottom row the MIRI. As you can see, the NIRCam observations are primarily filled with point sources, and these are stars or stellar clusters. The MIRI observations, on the other hand, show fluffy, diffuse structure. This is dust continuum emission, as well as emission from polycyclic aromatic hydrocarbons, or PAHs. You can also see that we are picking up very faint structures in between spiral arms. These are referred to as spurs and have not been seen very often in observations before. So the fact that we detect these strongly across all of our galaxies speaks to the sensitivity of the JWST and how it is fundamentally changing our view of galactic structure. Given that PHANGS-JWST is a treasury program, the science objectives are wide-ranging, but for simplicity, I've classified them into 2 main categories here. The first is the earliest phase of star formation, when young stars are still deeply embedded in their birth clouds. Because these clouds are very dusty, little light escapes from them in the optical, but they glow in the infrared, making JWST an ideal instrument for this science. These are primarily traced in the NIRCam wavelengths, but also the longer MIRI filters. The second science goal is the morphology and properties of the dusty interstellar medium, or ISM. This involves the study of the structure of the dust emission, both in continuum and PAH, as well as the properties of the small dust grains, such as their size and ionization state, and how this varies with environments. And these science cases have fundamentally different requirements on data quality. For the stars, we require excellent astrometry both between bands and to external reference images, and for the dust morphology, we require a good handle on level matching between different tiles in our mosaics and the absolute flux levels. So for this treasury, we have developed a tool that we call PJPipe. This is the PHANGS-JWST pipeline. It wraps around the official JWST pipeline developed at Space Telescope Science Institute, but offers a number of bespoke steps that we have developed specifically for our observations, although these are likely to be generally useful in a number of applications. These include tools for removing noise from NIRCam data, background matching between tiles in a mosaic, as well as more control over relative and absolute astrometry. So here is a flowchart showing how we use them in our data processing, and the blue outlined hexagons show the steps that are part of the official JWST pipeline. PJPipe can now be installed via pip, and we provide documentation to help users run it on their own data. So the article on the data release is mostly a description of the lessons we've learned during this treasury program and how we've overcome them. So I will highlight a few of them and note that these are problems for us specifically, but are likely to be similar for any JWST imaging observations, especially ones of nearby galaxies and Milky Way observations. So firstly, backgrounds. Our MIRI observations have dedicated background observations, which are required to remove thermal noise and scattered light from the data. These are required in parallel with our NIRCam observations. So unfortunately, one of our first observations, IC5332, had near-cam observations fail, and we only acquired the backgrounds many months after. In the meantime, we used the backgrounds from the nearest observation in time, which was NGC 7496. So from this, we discovered that the timing of when the backgrounds is taken is more important than the actual position in the sky. Using the dedicated backgrounds much closer in the sky resulted in a significantly worse final image, whereas using the backgrounds taken for NGC 7496 resulted in a pretty good final image. A major problem we faced with our near-cam data is that there is horizontal striping, and this is due to the way the data is read off of the electronics. So this is known as 1/f, or pink noise, and it's especially bad at shorter wavelengths. So here I show a typical single observation in the f200W filter. And we've developed two strategies to mitigate for this noise. The first uses only single tiles, and it filters out the large-scale structure that fills our images, leaving only small-scale structure behind. So this large-scale structure is both emission from the galaxy and it is noise at larger scales. But having filtered this out, we can at least build a horizontal model of the noise through a series of median filters and subtract it. And we do this for each of the 4 readout quadrants, which, as we can see, have somewhat different noise patterns. And on the right, you can see this approach is reasonably successful. The image is much improved and the small-scale noise has been removed, although large-scale rippling still remains in the data. So to remove this large-scale rippling, we take advantage of the fact that we have dithered observations, which means that we have multiple observations of the same position. So from this, we can build up an image of just the source. If the noise is mostly random, then by averaging over these dithers, the noise will cancel out and leave just the galaxy behind. So, having built up this stacked image of the galaxy, we compare it to each individual observation to create a map of just the large-scale noise, and we subtract this off from each tile. So following this, we have an image that is stripe-free, which you can see on the right. We also faced a number of issues with our astrometry, both between tiles in mosaics and to an external reference frame. And the problem arises because astrometry is generally handled by matching point sources between two catalogues. For the long Miri bands, we have very few point sources, so hooking onto an astrometric solution is difficult. For the shortest near-cam wavelengths, we actually have the opposite issue. We have simply too many sources, so cleanly identifying which ones match is very difficult. So we do a 2-pass solution to match between mosaic tiles and then to an external reference frame. So we first get a solution from a reference near-cam and Miri band, and other observations using this instrument inherit that solution. For the near-cam, we will then align again later for any residual shifts between tiles in a mosaic, although we measure these to be much less than a pixel. For Miri, trying to align these again actually decreases the quality of the astrometry, so we opt to not do that. Following this, we then have mosaics that have consistent internal astrometry, but this is not necessarily matched to an external reference frame. So we take catalogues of asymptotic giant branch, or AGB stars from the HST images, and these are red point sources, so they show up well in the JWST images as point sources. For near-cam, matching these is relatively simple, and it works well. For Miri, though, we often have no point sources at the longest wavelength, so we therefore get a solution from a shorter wavelength and we apply this to all of the mosaics. Overall, we find that the astrometry is very good. Residual shifts are, as far as we can tell, much less than the resolution of the instrument, and in most cases, much less than a single pixel. And we expect that this might improve in the future as we find better ways of selecting sources to match to external catalogues, but after extensive testing, this is the optimal solution that we have at the moment. Finally, because our observations cover the centers of galaxies, we typically don't have a true background to define a zero flux level. So, to get absolute flux levels, we compare to existing large field observations, which are either Spitzer or WISE if Spitzer imaging is not available. So by comparing the fluxes between similar filters between JWST and Spitzer or WISE, we shift our JWST flux levels up or down to match the images, which means that they would go to zero were our observations over a much larger area. And we find that this works well. We expect our fluxes are accurate to around the 0.1 megajansky per steradian level, and this is primarily limited by the data quality of the Spitzer or WISE imaging, so improving this may lead to improvements in the future. So, following our pipeline processing, we have 19 times 8 astrometrically aligned, flux-anchored, noise-reduced images that are ready for science. And about a year ago, we already published a number of articles on the first 4 galaxies that we observed, but with 19 now complete, we have a much larger parameter space covered and a much larger variety of galactic environments to probe. As well as this, we will also be observing another 55 galaxies in the next year of JWST observations, of which the first around 10 are already complete. And this will bring us a huge dataset that will enable many, many studies on star formation and link the local and global processes that drive galaxy evolution. So, thank you for listening, and if you want more details, please take a look at the pipeline paper, or if you want to download the data, it is now available via MAST.